This video will briefly introduce a low-profile broadband dual-polarization double-layer metasurface antenna for 2G, 3G and LTE cellular base stations. The relevant work can be found in IEEE transactions on antennas and propagation. The cross-polarized dipole antennas, majorly employed in mobile communication systems, use complicated feeding mechanism and structural modifications to meet the performance requirements. They also usually occupy a profile of quarter wavelength for unidirectional radiation pattern. Recently, introduction of metasurfaces in antenna design helps in realizing low-profile antenna, with the possibility to widen the bandwidth using surface wave resonance. Such a single-layer metasurface requires larger aperture size to realize wideband operation and in turn needs a larger reflector, which results in practical challenges. The low efficiency and limited interaction of the incident field with scatterers in a single-layer surface imposes difficulties and demands multi-layer structures. In this paper, an ultra-thin double-layer metasurface with optimized interlayer coupling is combined with a cross-dipole antenna. The reactive coupling of higher-order Foucault modes aids in the miniaturization of the metasurface. Operating the metasurface in the non-resonant region facilitates wideband phase compensation and encompasses the resonant frequencies of a conventional cross-dipole antenna despite the reduced profile. In addition, T-surface waves propagating in the orthogonal direction to the excited dipole and radiating at the ends is observed at the higher frequency band. This resonance is controlled by the metasurface dimension. A dual-polarized, double-layer metasurface antenna is fabricated to validate the proposed concept. The antenna with a profile of 0.15 lambda covers the target band of 1.71 to 2.69 GHz with isolation greater than 27 decibels. The average realized boresight gain is 9 dB with a plus or minus 1 decibel variation. The half-power beam width is 56 plus or minus 12 degrees in H and V plane. The radiation patterns show cross-polarization level less than minus 18 decibels, front-to-back ratio and side lobe level higher than 16.8 decibels. The simulated radiation efficiency is above 86%. To conclude, the proposed dual-polarized antenna incorporates double-layer metasurface to miniaturize the metasurface size and enhance design flexibility. In comparison to the conventional dipole antennas with a profile of 0.25 lambda, the overall profile of this antenna is reduced to 0.15 lambda. The bandwidth covers the 2G, 3G and LTE bands. More details of this work can be found in the reference. Thank you for your attention.
Hello everyone, this is a short presentation of paper A Broadband Metasurface Antenna Array with Ultra-Wideband RCS Reduction by Lina Chiu and Gaobiao Shao. Low scattering antenna design is a hot research topic. These designs focus on the RCS reduction performance, while the radiation performance of the antenna needs further improvement. On the one hand, metasurface is effective for reducing the RCS. On the other hand, metasurface antenna achieves wider bandwidth. As both structures are planar with low profile, which is easy to integrate, it is possible to combine these two features. This figure shows the schematic diagram. Regions A and C consist of the same type of cells. Regions B and D are composed of another type. This results in a chessboard structure that achieves backward scattering reduction. Regions B and D act not only as scattering surfaces but also as radiators. In this way, low scattering and radiation are combined. Cells with double-layer structure are used as the basic unit structure. The maximum phase difference bandwidth that can be obtained cover almost 6 to 26.5 GHz. This structure also demonstrates size flexibility, meaning that the size can be optimized to suit the antenna design requirements. For the radiator, a conventional 4x4 arrangement is firstly considered. The characteristic mode is utilized to study the radiation mechanism. The fundamental modes are Mode 1 and Mode 2, which are available to construct the radiator. Unfortunately, Antenna arrays constructed from this radiator exhibits radiation pattern distortion. Notice that the modal currents on the corner cells are relatively small for fundamental modes. A new arrangement without four corner patches is proposed that exhibits approximate radiation performance. Based on above structure, symmetric radiation can be achieved with chessboard-like configuration. Analysis results shows the selected modal radiation pattern is symmetric about the diagonal. After the introduction of an appropriate feeding structure, the overall structure of the low-scattering antenna array is finally obtained. The simulation model and the fabricated prototype are shown here. For radiation performance, such as reflection coefficient, gain and pattern, the measurement and simulation results are in good agreement. For low scattering performance, results show a significant backscatter reduction. Compared with other designs, this design method provides a good way to achieve broadband radiation while maintaining RCS reduction performance. Thank you for viewing.
In this video, we briefly introduce our working to metasurface antenna with co-circularly polarized radiation characteristics for wideband monostatic simultaneous transmit and receive applications. Further details can be found in IEEE transactions on antennas and propagation. The in-band full duplex, IBFD, also known as the simultaneous transmit and receive, STAR, technique allows a device to transmit and receive signals at the same time and on same channel or frequency, can double the spectral efficiency and system capacity. Compared to half-duplex, TDD and FDD systems. However, the expected doubling of capacity is largely limited by the self-interference, SI, between the collocated transmitter and receiver. To achieve STAR operation, the consequential SI should be sufficiently mitigated to over 110 dB, depending on applications. Generally, the high SI cancellation, SIC, requirement is achieved through a series of SIC techniques in antenna, analog, and digital domains. In this work, the metasurface antenna is for the first time used in designing a monostatic STAR antenna system. A series of works has been introduced to enhance the operating bandwidth and maintain a compact structure in the monostatic co-CP STAR antenna system. And the proposed feeding networks in this research achieve high isolation between TX and RX and improved performance compared to previous designs, offering wider operating bandwidth, lower imbalances, and easier integration into modern wireless communication systems. The proposed STAR antenna system achieves monostatic operation, wide bandwidth, co-circular polarization, high isolation between TX and RX, compact size, ease of fabrication, and low cost. The operating bandwidth is 4.5 to 6 GHz, with the isolation 36 dB. Besides, the TX and RX antennas exhibit the same RHCP radiation characteristics in the boresight direction, as well as similar radiation patterns. Within the operating frequency band of 4.5 to 6 GHz, the measured boresight gains are about 5.7 to 9.8 dBIC for TX, and 6.4 to 8 dBIC for RX, while the measured boresight ARs of the TX and RX are less than 3 dB. More details can be found in the references. Thanks for your listening.